ensemble methods consist of combining a number of hypotheses and then aggregating their predictions in order to obtain a prediction that, if things work well, is more reliable, has less error than individual predictions from the individual hypotheses. And we're going to look at two different approaches. There are actually many different examples of ensemble methods, but we'll just cover two examples to illustrate the idea, and we'll look at two examples that are focused on different aspects. So bagging, or a variant which is bragging, that basically focus on reducing bias reducing variance without sacrificing bias, ideally, and boosting, which is used basically to try to reduce bias by aggregating the different hypotheses. So let's see this general idea that the basic idea here is that if one classifier is making mistakes, maybe we can combine a group of classifiers and do something like a majority vote or a weighted average or something like that, that would improve classification, because now we're using different classifiers or different regression hypotheses and so on. And so using those different opinions and aggregating them could improve the final result. So the two approaches we're going to focus on is bootstrap aggregating or bagging, which uses bootstrapping to train a set of hypotheses and then combines the predictions. So this combination, we'll see, reduces variance because we'll be averaging over a large number of hypotheses. So basically this is good if we have models with high variance and we combine them in the way that reduces this variance while not sacrificing the ability of the model to adjust to the data. Boosting attacks the problem from the other side. So we have weak classifiers, and so weak classifiers tend to have a large bias. They will not have a large variance, but they'll have a large bias. But we'll use the weak classifiers to focus on different aspects of our data, on different sub-problems of the classification. We'll see how, and then combine them with a linear combination, and the final result tends to be more powerful than the individual ones. So basically we are attacking the problem of high bias and reducing bias without mainly having to sacrifice the error to an increased variance. So let's start with bagging, bootstrap aggregating. We're going to use bootstrapping to generate replicas of the training set, and this allows us to train the model over different replicas of the training set. So we will obtain different hypotheses. And now we aggregate the output of the hypothesis. For example, in a regression problem, we can compute the average or the median of the values that are being predicted. So let's go back to this typical example that I've been using. We have this data in this S curve, and we want to compute a regression, to fit a regression model to this data. But the problem is that we have a very high variance. So we are using a high degree of the polynomial, and if we train our model with few points, we can get a very large variance. So all these gray lines here are indicating the different curves we obtain when we train our model, when we fit the polynomial to each replica of our training set. So remember this method that we saw in the previous lecture, where we can take the data set, the data matrix, we create a large stack of new matrices with the same shape, but then for each one we're going to sample at random the points from our original data and fill in that random set of points. So we have this number of replicas which are all different from the original data and different from themselves because they have different combinations of points. And now if we train the polynomial, which has a large degree, so it can easily accommodate all these different values, if we train it for each of these replicas, we get a very wild fluctuation of curves here. However, when we are doing the prediction, we can do the prediction for all these different replicas and then average it by computing the mean. So when we compute the mean, we have this red line here that is a lot more stable. There are still some places where it can deviate a bit, but it's a lot more stable than all of these gray lines. So basically, when we are averaging over a large number of predictions, we are reducing variance, we are reducing that dispersion, because now we are taking those predictions and just looking at the average point. We can do a variant of this, which is instead, this is basically the same thing in all the code, so only here we would put, for example, the median. So instead of computing the average, the mean, we compute the median, which is the point at which we can split into 50% below, 50% above, and so we get something that is a bit more stable yet than the mean, because it's less sensitive to outliers. So the fact that we may have a few curves going very long downwards or upwards will not affect this as much. So this is called bragging instead of bagging, but it takes the median instead of the mean, and for the rest is exactly the same thing. So basically what we can do here is we take advantage of the fact that we are overfitting with our model, and our model is very flexible, and so that gives us very wildly different predictions. But when we average those wildly different predictions, we start getting something that is a lot more well behaved and gives us less error in the prediction. We can use this for classification also, but in this case we can take the majority vote of the different classifiers. So suppose we have a support vector machine. Actually, a support vector machine is not a very good classifier for this, because this works best with less stable classifiers. But still, if we reduce regularization, we can see the effect here. So we can create the replicas for our training set by bootstrapping, exactly as before. And now what we do is, for each replica here, we train the support vector machine classifier, and then we can retain a set of the classifiers already trained, but we can also do the predictions and then average the predictions here. So how can we take the majority vote? This is not a simple average, but if our classes are 0 or 1, then we can do that average. So you can average the predictions by dividing by the total number of replicas. So this is a vector with the predictions for all the points. This is the total number of replicas. We divide it, and now we obtain a value that will be larger than 0.5 if the majority of the predictions was 1, or lower than 0.5 if the majority of the predictions was 0. So if we round that value, we get either 0 or 1 depending on the majority vote. So basically this is similar to what we were doing with regression, the only difference is now we're taking the majority vote of all these classifiers. So these gray lines here are all the different results of the different support vector machine classifiers trained on replicas of the points. The reason why they have this dispersion is because each replica that we are considering here takes a random subset of points. So sometimes these do not appear, but they are duplicates of these red ones here, or vice versa. So it may be that sometimes the line is drawn here, or sometimes the line is drawn more to this side because there are more of these points and there are some of here missing. And this is happening at random when we generate the replicas by bootstrapping. But then when we take the majority vote, this averages out and we get this frontier here. So this thicker line and the division between red and blue is the division taking the majority vote of 50 support vector machines. One thing that you can note is that in the case, even with a very low regularization, so this is the value for C, and a large gamma to try to make the support vector classifier as flexible as possible. Even so, we notice that there isn't really that much of variance here. So we are improving things a bit with the majority vote, but we do not gain as much as we gain, for example, in this case with the polynomial regression. So this is because of the way bootstrap aggregating is working. If we have independent classifiers, that is, the probability of a classifier classifying correctly or incorrectly some point is independent of what the other classifiers in our aggregate are doing, then it's easy to compute what happens when we put several classifiers together, because we can look at the distribution of probability of, for example, the majority vote being correct. So if we start with classifiers that have a probability of 80% of getting the right answer, then even a few classifiers will bring us very close to 100% of getting the correct answer when we take the majority vote. But even with classifiers with the probability as low as 60%, for example, which is this blue line, as we keep approaching, for example, 100 classifiers, we are now very close to 100% of getting everything right. So this happens because we are, when taking the majority vote, even if each classifier individually is not very good, when we aggregate a lot of them, the average result tends to start approaching and narrowing towards 1. But this only happens if the classifiers are independent. This is an important issue here, because suppose that we have 10 classifiers that are all doing exactly the same. Then taking the majority vote is completely useless, because the majority vote is exactly the same as each classifier is doing. So basically, bagging is good for unstable algorithms, which means that algorithms that give you very different outputs depending on the inputs, the data set that you're using. For example, here we see that this is very unstable. Polynomial regression, when you use a high degree polynomial with few data points, it becomes very unstable. Support vector machines are not that unstable. So there is a stronger correlation between the classification of the different classifiers, which means that we're going to gain less by taking the majority vote. Okay? So this is an important aspect. Basically, if you have models that are overfitting, that have wildly ranging predictions, and that the different hypotheses are independent or more independent of each other, then bagging becomes a very good approach, because averaging those predictions or taking the majority vote can greatly increase your accuracy. If the hypotheses are strongly correlated, if they are telling you mostly the same thing, all of them, then you gain very little by using bagging, because taking the majority vote of things that are all equal will not improve anything. Now, for boosting, we'll be solving the other problem. So basically, you can imagine that bagging helps you solve the problem of having models that are strongly overfitting. If the model is underfitting, bagging is not very useful, because all of the hypotheses will make the same kinds of mistakes. Boosting is we can see it as the inverse of bagging, in this sense, that is trying to tackle the opposite problem of having classifiers that are very biased because they are weak classifiers. So the idea here is to learn a linear combination of weak classifiers. So weak classifiers are classifiers that are not very good. They must only have an error rate below 50%. But we are going to combine them and we train them in different ways in order that the combination provides a better classification because it lowers the bias on aggregate. So the way we do this is we need a classifier that can take into account different weights for different examples. And we start with all the examples weighing the same, and they weigh each one over the number of points that we have. So if we have 1,000 points, each example weighs 1/1000th part. Now we fit the classifier by minimizing the weighted error. So initially the weights don't make much difference because don't make any difference because they all weight the same. But what we're trying to minimize is this indicator function, which outputs 1 if the prediction is different from the target value, or 0 if it's the same. So basically we want to minimize the number of errors, but weighted by the points. So some points will be worth more than others and weigh more in this error function. And now when we do this minimization, when we obtain for one classifier the best fit for this weighted set of points, we now compute the weighted error on the classifier. So basically this is the weight of each point multiplied by 1 if the point is incorrectly classified. If it's correctly classified, then this is 0 and it doesn't count. And then divided by the total sum of the weights. If we keep the weights normalized, so if we make sure that the weights all add up to 1, we don't need to keep dividing like this, but the idea is that we have this normalized and we are computing the weighted average of all the errors. So this is the weighted error for the classifier after training, and then we compute the weight the classifier will have on the combination, because now we'll be building an array of classifiers. Each one will have its own weight, its own importance in the classification, and this is the weight for the classifier. The logarithm of 1 minus the error divided by the error. Just a small side note here that in the original paper this is 1/2 the logarithm of this, but most of the books use this. It doesn't make a difference, any substantive difference, and actually converges a bit faster like this. But you may see, if you look at the original paper, you'll see this with a slightly different formula. So now what we do is we train the first classifier like this. Now we're going to go on to the next one. And if we didn't do anything, the next one would be exactly the same as the first, because we're using the same data set. But we're going to update the weights of our examples. And the weights of our examples for the next classifier will be the original weights multiplied by e raised to this expression here, which is how much the classifier will have, the importance of the classifier in our final set, multiplied by this indicator function, which is 1 for each point that was mistakenly classified, and 0 for the points that were correctly classified. So basically e raised to 0 is 1, so all the points that were correctly classified will retain exactly the same weight. But the points that were incorrectly classified will be multiplied by e raised to some value here, greater than 0, so they will increase in weight. We can then normalize the weight, so to keep everything summing up as 1, but the idea is that some points will now become more important, and the points that become more important are the ones that were incorrectly classified previously. And now we're going to stop when the error we get here, so the error with the weighted points is 0. That means that we can successfully classify all the points in the training set. We don't need to continue. We can continue, but it's not very useful after that point. Although there is some cases there may be some benefit, but usually we stop when we can classify everything without errors, or if we have an error greater than 0.5, then something went wrong, because we should not use a classifier that gives us more than 50% error. That will not work. So, but basically, if things go right and we do this in the normal approach, we iterate this until we can classify all the points in the training set without mistakes. And now the output of this, so the boosted classifier, will be the weighted sum of all the classifiers. So it's a sort of a majority vote. When we want to classify a new point, we're going to go, run it through all the classifiers we trained, but we are going to give a different weight for each classifier, and the weight is the one that we computed here. Now we're going to add up all of these majority votes, all of these votes with different weights, and see what it points to, what on aggregate it points to. So if the classes are -1 and 1, we can simply take the sign of this sum here. So if this sum is positive, then the weighted votes of all the classifiers is leaning more towards class 1. If the sign is negative, then it's leaning more to class -1. If you use class labels of 0 and 1, then you need to modify this slightly to see if it's tending more towards over 0.5 or below 0.5, but the idea is the same. Okay, so let's see an example of boosting, which is called stamping, which uses decision stamps. They are decision trees with only one level. But to explain this, I'm going to take here a small detour and explaining the decision tree algorithm. So this is another classifier that basically will iteratively split data into two subsets according to one of the features and some rule, for example, some value below 1 or something like that, and do that in a way that maximizes some measure of information gain. So basically trying to make the two subsets as uniform as possible in the classes. So ideally one subset should have only one class and the other subset should have only the other class. There are different measures of information gain, for example, entropy, the Gini index, and so on. But the general idea is to try to split the data into subsets that are less mixed together and have ideally only one class there. So let's see an example for this problem. We could build a decision tree that would do something like this. So we start with our 90 points. These are 90 points, 45 red, 45 green. And we apply this rule. The first feature, so x0, which is the one here on the horizontal, is below minus 0.19. So this would be a line somewhere around here. If we do this, we have one set of 25 points that only contains red points. So this is done. We have because it's this part here, we can split here, and this part is already a single class in that set, so we don't need to worry about that one anymore. The other side still has a mixture, because if we split here, this side has a mixture of red and blue points. But now we can also split, if we split at 0.4, so it's around here, we can then divide. So this is 0.4 on the horizontal axis. So now if we split this side over here, we can separate these blue points from this part on the top. So this is this rule here that only leaves one red here among these 35. So this one is easy to separate. This is a bit more mixed and we keep separating, and this is the final result. So when we apply all these rules, we have this classifier that separates according to one feature or the other, choosing always the best feature, and generates these subgroups that contain only either red or blue points. Okay, so this would be the decision tree algorithm that has some advantages and disadvantages. By the way, one big advantage is that it's easy to understand what it's doing. We can actually look at the rules. But we are going to use boosting for this by using only decision trees of level 1. So you can consider only this first part here. We take the data, we separate into two. If we only use the first level, this is a very poor classifier. So it's a very weak classifier. It doesn't manage to get a very low error. But what we're going to do here is to compute the one classifier. We train one decision tree classifier with our data using these initial weights. So the initial weights are just one for each point and then divided by the total number of points. So we have 90 points, so each weight is 1 over 90. And we are training the first classifier in this way. Now we're going to compute the predictions. We're going to see which of them have errors. So it's 1 or 0. 1 if they have an error, if the prediction is different from the data. 0 if they are not errors. And now we're going to compute these expressions here. So the total error, the weighted error, and then the weight of the classifier, and update the weights of the different points. So this is what we're doing here. in this part. So this is the total number of errors multiplied by the weights of the points. Note that this errors array has a 0 if it's not a mistake, if the point was correctly classified, but has 1 if the point was incorrectly classified. So when we multiply this by the points, all the ones will have the weight and the zeros will not contribute to anything. So this would be the weighted error. And now we can compute the alpha, the contribution of this particular classifier to our boosted classifier, so the array of classifiers, and the alpha is the logarithm of 1 minus error divided by the error, and then we can update the values of the points. So the weights of the points are the previous weights of the points multiplied by multiplied by e raised to alpha times the errors. Note that this error is a vector. This is a vector too. So basically, points that were not incorrectly classified have a 0 here. And so if we raise e to 0, this is 1, and it does not change the weight. But points that were incorrectly classified at this stage, their weight increases, and so we update their weight in this way. So this is larger than 0, this will be larger than 1, and the weight will increase. And now we just normalize the weight so that the weights all add up to 1, and we don't need to keep, for example, dividing by the sum of weights. So if the sum of the weights is always 1, we can simplify these computations. So this is what we're doing here with this normalization. Okay, so now we append this particular stamp. So this is a decision tree with only one decision. It has a depth of 1. We append this to the list of hypotheses that we are keeping. And we append the alpha that we computed there to the list of weights for the different hypotheses. And we're going to do this 50 times. So we're going to retain 50 decision stamps, each one with its own weight. And this is what's happening. The first time we train, we get this decision, which is actually the one we got here, the first one when we trained the decision tree. You see, we are using feature 0, the first feature, and we are cutting at that minus 0.8. So it's this part here. We have one set of points, of red points, that are all correctly classified on this side. Now we are classifying everything else as blue, but now there is a mixture here. There are some red points here, and so the weights for these points will increase because they are incorrectly classified. So when we go to the second decision stamp, we now are classifying this data set where these points have more weight. So the second one will not choose the line here, it will choose the line here. And when we consider the two, we now have this classification, which is now classifying these points correctly, but these blue points are now being misclassified as red. So when we update the weights and we normalize, these ones keep shrinking because they've always been correctly classified. These ones are now a bit smaller because at the second classifier they were correctly classified. And now these ones are a bit larger because they were incorrectly classified here. And now we keep doing this. So we start this way. Each time we have different points that have different weights. So the decision stamps will go in different ways. And the aggregate of all these classifiers will result in different classifications. Until we reach a point where everything is correctly classified. So this is the boosted classifier that takes this combination of decision stamps with different weights and provides us with this classification. And the reason why at each step the stamps were giving us different classifications was because the weights of the points were changing along these iterations, and so they were pulling the frontiers more to one side or the other in order to try to fix the previous mistakes. So this is how to train the boosted classifier. Then we can apply it for classification like this. We have we can start with the 0 vectors for all the predictions. And now we're going to predict a set, the classes of a set of points. And what we do is we go through all the classifiers that we stored. So this array here has all the hypotheses that were trained, all the decision stumps. And we are going to loop through all of them and add the predictions multiplied by the corresponding weight. So each classifier has its own alpha that we computed here, and this is the weight that this classifier will contribute to the final classification once we finish training. So this is what we are doing here. We are multiplying the prediction. Of this classifier by its weight, and then adding that all with the previous predictions. So now we have this net prediction to which each classifier contributed in proportion to its weight, to the alpha value there. And if we have classes of 1 and -1, then for all cases where the prediction is below 0, so adding all the weighted votes of all these classifiers, if it tended towards less than 0, then this will be class -1, and if it's more than 0, this will be class 1. So now we can compute the errors and so on, but this is how the boosted classifier works, by taking into account all the votes of the different small classifiers we combined, each one weighted by its own weight. So they are not all voting equally, they are voting with different weights depending on the alpha that was computed for each one. So another way of looking at AdaBoost, so in this more procedural way, we are seeing AdaBoost as a method of training classifiers, different classifiers, and then bagging them all together in the same array and taking the majority vote by the weights. But we can also think of AdaBoost as training one complex classifier that is a linear combination of these smaller elements, and was trained by doing a stepwise minimization, so a sequential minimization, each sub-classifier at a time, trying to minimize this exponential error function. So this is the true class, the prediction that we have. So for point n, we have this prediction f, and we have the true class t. If the value, if they have the same sign, so if the class is -1 and prediction is for class -1, or if it's 1 and 1, then this product will be 1, will be positive, and this will weigh on the error function with a small value, because it's e raised to a negative number. But if the classes and the true value diverge, if one is -1 and the other is 1, then this product here will be negative. Because we have the negative side, now it becomes positive, and so it weighs more on the error function. So let's suppose that we have this exponential error function that is penalizing errors in classification, and we are trying to train one complex classifier that works like this. So it's the for m sub-classifiers, it's going to take the weighted average of or the weighted sum of all the classifications of each individual classifier. So if we have 50 classifiers, then the classification is this weighted sum of the 50 classifiers, just like we saw before. But now we are imagining this as one single classifier, and we are training to find these alphas here that give us the different weights of the different classifiers, and also training to find the particular classifier, how to optimize its classification. But the trick is that we're not going to do this all at the same time, because that would be too complex. We're going to do this one at a time. We're going to start with the first classifier, then we consider the first classifier to be constant, and we add the second one, and then the third one, considering the first two to remain constant, and so on. So when we are at classifier M, we assume all those before to be constant, and we are only optimizing for M. So we're going to minimize this error function for the last one. I'm going to skip a bit quickly over the derivation, because the idea is not the demonstration itself, but to understand the boosted classifier as a single classifier and not that first approach of a set of different classifiers. So let's take this exponential error and separated it into the correctly classified and incorrectly classified. Because if it's correctly classified or incorrectly classified, this product between t and the prediction, so the class and the prediction, will be positive if it's correctly classified, negative if it's not. So we can separate between those that are correctly classified, in which the contribution to the error is small because of this negative sign here, and those that are incorrectly classified, which have a larger contribution to the error. We can rewrite this by adding a small contribution to all of the points and then adding the difference only to those that are incorrectly classified. And for this we can use this indicator function that is 1 if they are wrong and 0 if they are right. So basically this is just rewriting the same expression, but to show that we can use a constant factor here that does not depend on our classifier and just adds this base number that is contributed by all the points independently of whether they are well classified or not, but then has this extra penalty for all the points that are incorrectly classified. If they are correctly classified, this is 0, so they don't penalize anything. But if they are incorrectly classified, this is 1. And the added penalty is just the difference between the penalization if it's incorrectly classified minus if it was correctly classified. So when we do this, we see that when we're trying to optimize our classifier M, it's only this part that matters because the rest is constant. So for optimizing classifier M, we only need to worry about those points that were incorrectly classified at this stage. And then for minimizing with respect to the alpha, so this weight that we have here, we get this expression where the error is the weighted error for all the points. So basically, this is the same thing we found. We want to train each classifier to minimize the number of errors multiplied by the weights of the respective points, so the weighted error in this sense. And we want to compute these alphas in this way, the formula that we have there. So what this means is that we can think of AdaBoost as one classifier that we are training by sequentially optimizing individual parts until we find the best linear combination of those parts. So the idea here is not for you to memorize the demonstration, but to think of AdaBoost as more than just combining individual classifiers. We can think of it as one complex classifier that is a linear combination of all the others. Okay? So to sum up, we saw two examples of ensemble methods. Actually, there are many more examples of ensemble methods, but we focused on these two. And bagging, we are averaging the predictions or taking the majority vote, which is very good for overfitting or for independent models with high variance and low bias, or sorry, independent hypothesis. So if the model can generate independent hypothesis and the model has a high variance and a low bias. So basically, if the model is overfitting, bagging is good because it tends to be more independent. Note that if there is a large correlation between the different hypotheses, then bagging doesn't work very well because now it doesn't matter if we average all of these, it won't make much of a difference. And the way we obtain different hypotheses using the same model is by bootstrapping. So we create replicas of the training set and we use those replicas to generate different hypotheses. Boosting is different. We are using weak classifiers, so they generally will have a large bias and not be very capable of fitting the data. But we are combining them with different weights. So we are looking for a linear combination of these classifiers that makes the whole thing work better than each individual classifier. We are not using bootstrapping, and the reason why the hypotheses turn out differently at each iteration is because we are changing the weights of the examples. So boosting works when we can give different weights to different examples in our classifiers, and that's why, for example, this decision trees using only the stamp, the first layer of the decision tree, is a good option because it's very easy to change the weights there. So basically it's good for models with a high bias because now we are aggregating them in a linear combination that will become more powerful than the individual models. So for the first test, we'll have this part of the subject matter, so lectures up to this one. And the next, I think it's 2 sessions or maybe 3. The test is only in mid-November, so there's still a long way away. But I'll make the last session before the test a session for revisions. So until then, the lectures that you're going to see before the test will not be covered by the test. So the first test is only for lectures 1 to 12. This I forgot to update. This is not November 5, but I will let you know the exact date. And well, so sorry, I forgot to update this slide. This is still pre-COVID. So you can the test will be done. Basically, we can. I will update the slides when I upload this lecture. But these were the rules for when we were doing it on paper. You could bring your own material for consultation, so one A4 sheet. In this case, you'll be doing the test at home. You can look up anything that you want, but you will have questions that are timed. So you have a time limit for each question, and you don't have much time to look things up. Now, the important thing is that the exam will be scored in 2 independent parts. So if your first test doesn't go very well, you can still do the second test, and then in the exam you can focus only on the first test if you want. Or you can do both things. So the way this works is that the exam is the same for everyone, but you know that you have the grade of the test as a minimum grade for each part of the exam. So if you had a very good grade on the test, you don't need to worry too much about that part on the exam unless you want to improve it. Now I'm planning to include questions for assignment 1 on the test, but I'm not at the moment. I'm a bit undecided because this is what we've been doing on previous years, to include one question at the end of the test to evaluate the student individually about the participation on the first assignment. And this tended to work well because then that will affect the grade of the first assignment, and we can make some distinction between the 2 partners on the group. However, in this case, the test will be very late, so it's still about 3 weeks away. And this means I can only grade the assignments after the test, so this probably will not be convenient. So this is an issue I'm still trying to decide if it includes questions or not for the first assignment. But in any case, I will decide this in the next few weeks, and I will give you the detailed instructions for the test. But the 2 important things to retain here is that the first test is only for lectures 1 through 12. So until this lecture, the next lectures will not be on the first test. They are for the second test. And the exam will be scored in 2 independent parts. And the grade for each test is guaranteed on each part. So you have the grade for the first test as a guarantee on the first part of the exam, and the second test on the second part of the exam. So this can help you decide if one of the tests doesn't go well, you still can benefit from coming to the other test. So to sum up, we saw these 2 approaches to ensemble methods, bagging and boosting. Basically, bagging is good for reducing variance when the models have large variance and give you independent predictions. If there is too much correlation, if your model produce hypotheses that are too correlated when you do bootstrapping, then this doesn't pay off because you're averaging things that are all the same. Boosting, you basically try to reduce bias by combining different simple classifiers, and this works by varying the weights of the examples in order to train the classifiers differently, so different hypotheses generated from the same model. And it's useful when you have a large bias and you can reduce the bias in this way. But this only works if your classifier can handle different weights for the different examples. Okay, so I'll be moving on to the Zoom meeting, so we'll see you soon.